All right. Hi, and welcome to a bit about bytes, about looking at Python bytecode. So in addition to being a clever play on words, should be some useful information. So without much further ado, we have James Bennett, a Django core developer. So let's get the talk underway.
Hi. So I want to start with sort of an existential question. Why are we here at PyCon? We're here because we love Python, right? Right? And why do we love Python? We love Python because we all understand this great truth of programming, that we read code much more often than we write it. And so we should write our code to be as readable as we can make it. And of course, we love Python because Guido gave us a whole language built around that simple idea that code should be easy to read. And that language is Python. Clear, easy to read, understandable Python. Even people who aren't necessarily programmers can at least look at some Python and follow the logic of what's going on. Right? Okay, so this actually is Python, or at least this is how Python works. If you go download Python from python.org, you get what we call the CPython distribution. This is how it executes your code. We're going to learn about where this comes from, how this works, what sorts of useful things we can learn from understanding it, and how we can apply that, both practically and in a sort of theoretical sense. But before we do that, we need to understand a little bit about how computers work, and we need to understand a little bit how programming languages work. Now, I love this because it is beautiful and it is true. But we do need to understand how a computer actually works. Deep down inside, you have your CPU, your processor. It's a little wafer of silicon, and inscribed on it are these electrical circuits. And they're set up so if I send a certain pattern of electricity in, I get another different pattern of electricity out. It's very predictable. And we give names and meanings to these patterns. We treat them as if they do mean something. So we say this pattern of electricity actually means add two numbers together. That's how your computer actually works. Those names we give to them, we call them instructions for the CPU. Sometimes you hear them called machine code for the CPU. If we show it in a slightly more human-readable format, you'll sometimes hear it called assembly. But it's not all that friendly to humans to look at this stuff. Anybody ever looked at assembly? How many of you would like to write like that all the time? So you want to write source code, which is the beautiful, clear, easy to read, easy to understand, human-friendly version. But your computer wants these binary instructions. So how are we going to get from one to the other? There are some options. There are some different ideas that have been tried over the years. Some languages, you're going to run a program called a compiler, courtesy of Rear Admiral Grace Hopper, which will take your source code and transform it directly into those machine code instructions. We call those compiled languages. Some languages, you just invoke the language itself with your program. It runs your program directly translating source code into machine code as it goes. We call that an interpreted language. People often say Python's an interpreted language. We talk about a Python interpreter. But there's actually a third way. Some languages compile to a set of instructions that's not for any real physical CPU that exists. I suppose you could go build one, but it doesn't exist right now. These languages compile to instructions for the CPU that doesn't exist, and then the interpreter is a piece of software that implements that CPU, that understands those instructions and how to translate them into the specific instructions for whatever actual processor you're running it on. We call that bytecode. There are a lot of languages that do this. Anybody ever use Java? Java compiles to bytecode. You run it on the Java virtual machine. Anybody ever used one of the .NET languages, C#? C# compiles to bytecode, runs on the .NET VM. And Python. Python compiles to bytecode, which runs on the Python virtual machine. So let's take a look at how this works. We're going to look at Python function. This calculates Fibonacci numbers. So this should be pretty easy to understand. We just got, a little if we're less than 2, return, otherwise, loop, figuring out what the next Fibonacci number is, eventually return it. How will Python actually execute this function? Well, has anybody ever seen a file with an extension .pyc? Especially if you use Python 2. Python 2 used to drop these directly next to your source code in the same directory. Python 3, we have a directory called pycache with double underscores. That's where your PYC files go. You may have heard these described as, compiled Python, or some sort of, time saver for when you rerun it again. That is Python bytecode. That's what's in that file. It's actually the binary bytecode that Python compiled your source code into, so next time you run that, or next time you import that module, Python doesn't have to compile it all over again. But that's the actual form that Python wants that code in order to be able to execute it. So how could we get at this and understand what's going on? Well, suppose you typed in that Fibonacci function into a Python interpreter, and you looked at it. It's a function object, and it would have this little attribute on it, _code. This is a Python code object. Did anybody go to Emily Morehouse's talk yesterday about parsing and the AST? It was a really good talk, and you learned a little bit about code objects and how Python uses them. We're going to look at some slightly different attributes than what Emily was talking about, because we're looking at the other side of this, is what happens after the parsing. So this code object, this contains everything Python needs to execute the function, and it has attributes we can poke at to see how it's going to do that. So one interesting attribute is called coconsts. This is a tuple. It contains all of the literal or constant values that were referenced in the body of our function. So we see our integers, we had a 2 in there, we had a 0, we had a 1, we had a tuple of a 0 and a 1, and we have none. Now none is kind of weird to see there, because the body of that function didn't include a literal none anywhere. But Python put it in there anyway. And there's a reason for that, which is if Python is executing our function, and it finishes executing without reaching any explicit return statement, it's going to return none. So Python needs to have none already loaded up, already ready to go in that tuple so it can reference it. Because at the time Python is compiling this, it has no way of knowing whether any explicit return statement is ever going to be reached. In fact, that's a really hard/impossible thing to do in advance. So these are our literals. There's another one called covarnames. This is a tuple containing the names of all the local variables of the function. We had 3 of those, n, current, next. So they're all in there. And then we have this one called conames. This would be any non-local names that we referenced in the body of the function. Now, the Fibonacci function didn't include any non-local names, so this is an empty tuple. And finally, we're going to get to the fun part. code. This is the bytecode of the Fibonacci function. This is not a string. This is a Python bytes object, because this is being done in Python 3 like it should be. Some of these characters do print, or some of these bytes do print as ASCII characters. That's just because that's how Python defaults to representing a bytes object, but it's not a string. We can't treat it as a string. It's a sequence of bytes. Now, suppose we want to understand what's going on in this big, long sequence of bytes. Well, we can look at it. That first byte printed as a pipe character. Now, I don't know about any of you. I have not memorized an ASCII table. So I don't actually know what decimal byte value produces a pipe character in ASCII. Fortunately, I can ask Python, and it will tell me. Python will tell me the pipe character is decimal value 124. So the first byte of that bytecode was a byte with value 124. Well, that still doesn't tell me very much. Luckily, there's a module in the standard library called dis, with this list in it called opname. It's a list of all the Python bytecode instructions. And at each index is the instruction name that goes with that decimal value. So it's the 124th bytecode operation. It's called load fast. Okay, so now we know the first byte of this is a decimal 124. That's a load fast instruction. The next byte of it was a 0. So it's a load fast 0. I don't know how much attention you paid to that first slide, but that's what it started with. load fast 0. That's a Python bytecode instruction. And specifically what this means is look up in that CO varnames tuple whatever item is at index 0, which is local variable n. Push that on top of the evaluation stack. We're going to get to what the evaluation stack is in just a minute. But first, I'm going to show you the shortcut. I showed you the hard, laborious way to read bytecode. Here's the easy way. Use the dis module, import dis, call the function dis.dis. You can pass in almost anything you want to. Here I'm passing in a function. You can pass in strings of source code. You can pass in all sorts of Python objects. And this will disassemble them, print a human-readable version of the bytecode that they compile into. And what you'll get out of that from that Fibonacci function is the contents of that first slide. This is the bytecode of that Fibonacci function. There's a couple things that are worth knowing here. This output you'll see over on the left, you'll see these numbers 2, 3, 4, 5, 6, 7, 8. Those are the line numbers in the source code. That's where each line's instructions are beginning. You'll notice each line of Python source code turned into multiple bytecode instructions. And then each instruction has a number next to it as well, and they're always even. Does anybody want to guess why that is? This is new as of Python 3.6. Those numbers are the offsets into the bytecode. If you grabbed that bytes object, CO code, on that code object, and indexed into it, say go to index 6, you would find a pop jump if false opcode there. The reason that those are even numbers is as of Python 3.6, not every bytecode instruction actually uses an argument, but as of Python 3.6, they all get an argument whether they want one or not, because that makes every one of these exactly 2 bytes, which makes it much easier to work with. There are some instructions that if their argument gets too large to fit in a byte, can actually split over multiple bytes, but it's always a multiple of 2 bytes. If you're looking at Python 3.5 or earlier, and you put in this same function, you might see some odd-numbered offsets because not everything actually got an argument in Python 3.5. One other thing worth noting here is we see some right-pointing angle brackets. We see them like line 4 offset 12 at that load const, line 5 offset 22. Those are jump targets. This is Python telling you these are instructions that may be jumped to by some other instruction that's going on here. So you remember that Fibonacci function had a loop in it with a test at the beginning. Every time we go to the beginning of the loop, we're doing a jump back to an earlier instruction. Those angle brackets are just there to tell you these are potential jump targets of other instructions. So now we've seen some bytecode. We understand how we can actually get at the raw bytecode as bytes, how we could decipher it manually if we wanted to, and now we know the easy shortcut. We've got to actually talk about how Python works, how it uses bytecode. So Python's VM, the virtual machine, in CPython is stack-oriented. It's built around the stack as a fundamental data structure. If you've never worked with stacks, they're sort of list-like, but they support 2 very important operations. A stack has 2 ends, which we'll call a top and a bottom. You have a push operation, which means take this value, put it on top, and a pop operation, which means take whatever's on top, remove it, return it. Each time you call a function in Python, you're pushing a new entry, a call frame, onto a call stack that keeps track of every function being executed. When one of those functions returns, that call frame gets popped right back off the stack. The return value gets pushed into the calling frame. So, if somebody calls our Fibonacci function, as we'll see in a minute, we get that return value back. Now, while you're executing this, in that call frame, in the call stack, we're going to use 2 more stacks. One is an evaluation stack. Sometimes you also see called a data stack. This is where Python is going to keep all of the data it's actually working with. This is where most of the execution happens inside a Python function. Most of the instructions are about manipulating what's on top of that evaluation stack. There's also a second one called a block stack. A block stack keeps track of how many different blocks are active right now. Blocks are things like a try except, with block, anything like that. Python needs that because there are some statements like break and continue that affect whatever the current block is. So Python needs to know what is the current block. And it does that by simply managing a stack. Like every time you go into certain constructs like this, it pushes a new item on the block stack. When it finishes, pops that item back off. So let's look at how we execute a function. Suppose we want to know the 8th Fibonacci number. We're just going to ask Python to calculate that using our Fibonacci function. That turns into 3 bytecode instructions: load global, load const, call function. So let's take a look at what's going on here. We start this, we've got an empty evaluation stack. So we get to our first instruction, load global. We're going to load the global name fib, which is our Fibonacci function. This is what's going to go look in that CO names tuple, that tuple of non-local names. It's going to look up that function, push the function object on top of our evaluation stack. Next, we're going to have a load const. In this case, it's going to get the first item out of our tuple of constants, because remember, index 0 is none. So the first item in there at index 1 is the integer 8, which is going to be the argument to our function. Push that onto the stack. Then we hit a call function instruction. Has an argument of 1. The way Python is calling this function, we're only using positional arguments, is it pushes the function onto the stack, pushes the positional arguments on top of it, then call function. The argument is the number of positional arguments to the function. It pops all those off. It knows the function is the next thing there, pops that off, pushes a new stack onto the call frame, or onto the call stack, executes our Fibonacci function inside that new frame, gets a return value of 21, pops the call stack, get that frame off, return value goes onto the top of our evaluation stack right here where we called the Fibonacci function. And that is step by step how Python is going to execute this function. Now the call function instruction is only for function calls that involve positional arguments. If you used keyword arguments, there's a different instruction called call function KW. If you use any of the iterator or mapping unpacking syntax, the asterisk, double asterisk syntax in your function call, there's one called call function EX that gets used to do that. So that's how we're executing a function. Now, if you want to, you can go dig into the Python standard library documentation. The dis module is extremely handy. It has a list of all of the things in the module, all of the bytecode instructions, what they do, what kind of arguments they take. Anything you could want to know about how Python bytecode works is all in there. There are a couple things I want to point out, though. They're kind of cool. One is another function that's in that module. It's called distb. How many times have you looked at an exception and wondered, well, where the heck did that come from? What made that happen? Well, this function, dis.distb, you can call it either right after an exception has occurred, or if you have a Python traceback object that you've captured somehow, you can pass it in. And what it will do is disassemble whatever call frame on the call stack was active at the time, show you the bytecode that was being executed, and give you a pointer specifically to the instruction where that exception got raised. So for example, here you can see I divided by 0, oops, Python raised an exception, import dis.tb, and here I can see exactly what happened. If you really want to understand what's going on, I'm going to have a link at the very end to where you can go look at the actual internals of the Python interpreter, which are written in C. This is the beginning of the actual, real, honest-to-goodness Python bytecode interpreter as it existed on GitHub about 2 hours ago. It is a gigantic switch statement that simply looks at whatever decimal value instruction was passed into it and figures out what to do with that. So, now we know some things about bytecode. But what can we learn from this? What use is it? What good is it to us to know about bytecode? Has anybody here ever written any forth? Or if you're a little newer, maybe played with a language like factor, or heard of languages like forth and factor. These are what are called stack-oriented programming languages. Python virtual machine is also stack-oriented. We saw this. It all orients around pushing things on top of a stack, manipulating the top of the stack, popping things back off. This is a very different way of doing programming than what we're used to, but there have been entire languages built around it. And understanding this way of programming is actually kind of cool. You may never even get any practical use out of it, but it's a thing you can learn, and it's a thing that will broaden your understanding of different styles of programming and different ways you can do programming. And it really is amazing if you look at a stack-oriented language or a stack-oriented virtual machine to see just how much you can do with so few instructions and so few basic operations on a stack. It's actually really, really neat. Of course, there are also some practical purposes. People like to joke about C. They like to call C a sort of portable assembler or portable assembly language because you can write C and read C and reason pretty well about what kind of machine code a given bit of C is going to turn into. Python is sort of the same way. We can learn Python bytecode and learn how to understand it, and then we can reason about what kind of bytecode is Python going to turn my source code into. How is this actually going to execute when I hand it off to the Python interpreter? Studying that can give you some insights. Also, you can learn a bit about how Python works and how Python can help you. And then, of course, what everybody wants to know is how you can look at it and reason about performance. So here's a couple of functions. Both of these do the same thing. They both calculate the number of seconds in a week, except one of them is faster than the other. Can you guess which one it is? I've very cleverly hidden it. I want you to stop and think, why would one of these functions be faster than the other? And how could we figure out why that is? And the answer is we can look at the bytecode. We can ask the dis module to disassemble these for us. There's a big difference in what those turn into. If you notice that first one stored the number of seconds in a day in a variable, which meant we had to load a constant, store it in a variable, then look up what was stored in a variable, load another constant, do a multiplication, and finally return the value. The second one only used multiplication with two integer constants, and Python, when it was compiling this, noticed we're using arithmetic on two integer constants. They're not going to change. The values of 7 and 86,400 are not going to change anytime soon. So Python can just optimize that away. Python can do that multiplication at compile time, and now this function is just return 604,800. There's nothing else to it. So that's kind of a cool optimization. Python will do that sort of constant folding anytime you have these operations on constants that it can optimize away. It isn't the only sneaky optimization Python does. Has anybody heard about Specter and Meltdown? Anybody familiar with those? These were attacks against branch prediction, where processors try to predict what's going to happen on the other end of an if statement. Python actually tries to predict what bytecode operations will happen. Some bytecode operations come in pairs, like a comparison is usually followed by a jump instruction of some type. And the Python bytecode interpreter optimizes this and tries to predict what's going to come next in order to work with your CPU's branch predictor to make these run even faster. So there's some cool things going on here. You can also answer some perennial questions about Python performance. People always ask things like, well, why is a literal list or a literal dictionary faster than calling list or dict? Well, right there's your answer. We just do a literal dict using that brace syntax. That's 2 instructions. If we actually call the dict function, that's 3 instructions, and one of them is a call instruction. So we actually have to push another frame on the call stack, execute a function body in there, pop it back off. You can see this in your own code. Like, here's a simple example. This is just a function that calculates the first 10 perfect squares. And this isn't the whole bytecode. This is just the body of that loop, that while loop. It's 15 bytecode instructions long. We do better than that? What if we change that while loop with a counter to a for loop with a range? Well, suddenly that's a much shorter loop body. Now it's 9 instructions. What if we go really idiomatic Python and say, oh, this really ought to be a list comprehension? What's that going to turn into? Now the whole function body is 9 instructions long. But this is deceptive. This is why I put this up here. Notice it's 9 instructions, but it involves building a function and calling a function. So it has to push another frame onto the call stack, execute another function body in there, pop it back off, return a value. That's a slightly more expensive operation. Even though this is fewer bytecode instructions, not all bytecode instructions are equally expensive to execute. So this is where we start talking about comparing different bytecode and different bytecode operations, and people always want to know about these micro-optimizations. The very first thing I want to tell you is Python is slow. If you're worrying about how fast a Python bytecode operation is, you're probably missing the forest for the trees, because Python is so much slower than C that it's not even worth worrying about that kind of micro-optimization. If you want to learn how to write really fast Python, really blazing great performance Python, the first thing you should do is take a good look through the standard library, standard modules, built-in functions and classes, find out which of them are implemented in C versus which ones are implemented in Python. Because the speed difference there, like some of these bytecode instructions, you might gain, this much, whereas getting it in C, you're going to gain this much. It's just no contest. But you probably want some general guidelines. So here are a few. Have you ever seen a Python optimization guide that says don't refer to names inside a loop, always alias it to something and then refer to the alias inside the loop? This is why. Not all load operations are equal. Load const and load fast are very fast. Load name, load global are comparatively quite slow. Going into the details of why, it's because the lookups for non-local names can be fairly complex. It may have to search in multiple namespaces before it finally finds what it's looking for. If you go look at the actual interpreter implementation, you can see the implementations of these instructions are pretty large. Another thing, loops and blocks are really expensive. Avoid them if you can. You'll see these instructions sort of jump out at you: setup loop, setup with, setup exception. Anytime you enter or exit a loop or a block or anything like that, you need multiple instructions to get into the loop, set up all the context, push onto the block stack, execute the body of the loop, jump back if you're doing a loop that jumps back, then finally pop everything back off and clean up. That's an expensive operation. Avoid that one if you can. Attribute accesses, dictionary lookups, list indexing, all of these things really stick out in bytecode. These load adder, binary subscript, this is another one you'll see people say. If you need something out of a dictionary or something out of a list and you're going to loop and you're going to refer to it every time through the loop, alias it to a local variable before you do that, because otherwise you're doing this expensive lookup every single time through the loop. These are relatively expensive bytecode instructions. A lot more of this you can learn by sort of looking through the documentation for the dis module, look at all these different operations and what they do. There are also some good resources. I'm going to recommend 3 here. One is there's a free online book called Inside the Python Virtual Machine. You can read it at no charge. You can also pay some money to the author to thank him for writing it. This is a complete tour of how Python works. Inside the Python interpreter, all of the internal mechanics, all of those stacks, all of the bytecode operations, the whole thing. Alison Kapter has written a Python interpreter in Python. She walks you through, and by the way, she gave a great talk here at PyCon. She walks you through how to build a Python bytecode interpreter with all the correct data structures and handling all of the bytecode operations in Python itself. And then finally, of course, you can read the bytecode interpreter, which is that gigantic switch statement that I showed you part of earlier. That switch statement, I think, is around 1,000 lines long, or at least it was in one version that I looked at. It is definitely hundreds of lines long. But you can actually read through it. It's fairly clear, fairly well-written C. CPython source code tends to be on the readable side as C goes. So all of those are really good resources. Also, if you want to, I am on Twitter. I will be heading out of here. I can take maybe 1 or 2 questions in the hallway afterward. And you can find me online and follow up. So, thank you all for showing up. Hopefully you learned something.